Morning everyone, hope you're staying safe. Starting to get a bit windy here, but not too bad at the moment. I'm going to do two videos today actually. You've got all half term to consume them, haven't you? So there's no sort of desperate rush. But the first one is going to just finish off the work we've been doing on mechanics with resolving, sliding, friction, and it's going to just look at vectors. So particularly vectors applied to F equals ma and suvat problems, Newton's second law, things that are accelerating. And then later in the day I'll do a revision video on moments, and that is just to sort of help support you in your revision for the second assessment. However, it is important that you all watch that because it links moments with friction, and the pre-release information for the summer exams has moments and friction in the same bullet point. So my implication from that is that it will be a question that involves both moments and friction. Okay, so here we go. We are going to start by talking about vectors. So far, when we've been talking about forces, being applied to boxes, those forces have been, a force of 15 newtons at an angle of 30 degrees. This is a repeat of the lesson I did yesterday to Grace's group, so you might want to fast forward a bit. But we say, right, okay, so when I resolve horizontally, that force has an effect of 15 cos 30, but that force also has a vertical effect, and that is 15 cos 60. However, we may choose to write that as 15 sine 30. Now what vectors do is they do it the other way around. Rather than giving us the magnitude and direction of the force, they give us the horizontal and vertical components. So it might be that this force is a force of 4, 2. And what that means is it's a force of 4 newtons in the horizontal direction and 2 newtons in the vertical direction. That can also be written in unit vector form. If you remember, I is a vector of 1 unit in the horizontal direction, so 4i is that, and j is a unit of magnitude 1 in the vertical direction. So these two are the same thing, and you may remember I prefer vector notation. And so what we can do in these cases is we can work out the magnitude and angle. So this force looks like that. So I can use Pythagoras to work out the magnitude. So that's 4 squared is 16 plus 2 squared, so that's root 20. And I can work out the angle of that force because it's 10 to the minus 1 of 2 over 4. And I guess I really should know what shift tan of a half is, but I'm going to do it anyway. So shift tan 0.5. So that's actually, no, I think I've been forgiven for not knowing that one. There we go. So that's all good. And what I did yesterday, so that's with my 13B group, the group I see on Thursday, is we recapped vectors in equilibrium, and we had done that with the other group, with the Jacob group, a couple of weeks ago, but you might want to look at yesterday's video, and I'll link that in the description below before you go ahead with the rest of this. Okay, so vectors talk about forces in terms of their horizontal and vertical components, but we can use vectors with more than just forces. So let's think about F equals ma, the formula we've been using when we're dealing with things which are accelerating, where the forces are unbalanced. Well, we're saying force is a vector, so I could describe that with some vector. Mass isn't a vector. Mass just has a size. We call it a scalar, don't we? But acceleration is a vector. So I can talk about the magnitude of acceleration, but I can also talk about it in vector form. What's the effect of that acceleration in the horizontal and the vertical direction? And let's think about suvat. Displacement can be described with a vector, because displacement has a magnitude and a direction, so I can describe that as a vector. Initial velocity, well, velocity has a magnitude and direction, so I can describe that as a vector. Current velocity also can be described as a vector. Acceleration also can be described as a vector. Time, not a vector. Okay, we can debate about whether time is unidirectional or whatever, but no, it has a magnitude but not a direction. So time is a scalar. So we can use F equals ma, and we can use Suvat equations using vectors as an alternative to using magnitudes, and that's what we're going to look at in this short video. Okay, so let's have a look at a question then, and then there's a couple from the book to try. And those of you who were in yesterday's lesson in Grace's group, you'll probably be smiling at this point, because I'm going to do a better job of it than I did yesterday, particularly at the end of the lesson when I got myself in a bit of a pickle over vectors. But yeah, so hopefully I'll make a better job today. So here we've got two forces, all right? And the great thing about vectors is that normally when we are dealing with forces in lots of directions, we've got all sorts of cos and sine stuff going on here. Forces in one direction take away forces in the other direction. But with vectors, it's really easy, because all I need to know is, right, what's the overall effect horizontally? Well, it's 12 take away 3, so that's 9. And what's the overall effect vertically? Well, it's -4 plus 16, so that's 12. So that's the resultant force. And, you know, I could have done that as a sum. I could have written it as 12 minus 4 plus minus 316, but I chose to do that in my head. Okay, so that's the resultant force. This is an unbalanced force. We're not in equilibrium. If it was equilibrium, this would equal 0. So we're going to get an acceleration. The particle has a mass of 3 kilograms, and acceleration is a vector. So I'm hoping you can see that the acceleration is going to be, because 3 times 3 is 9 and 3 times 4 is 12. So find the acceleration of the particle as a vector. Well, it's that. If it had asked me for the magnitude or the angle, well, I would have had to have done my little and worked it out. So the magnitude of that acceleration is going to be 5, and the angle, well, it's going to be whatever shift tan of 4/3 is. Okay, so let's now look at part B, the velocity of the particle after 7 seconds. Let's have a quick check of the question. It accelerates from rest, so we know that u is 0. So I'm going to set up my Suvat here. I'm going to have to move down, so yeah, I'll tell you what, I'll just fold that over. Okay, so I know that its initial velocity was 0, but because we're dealing with vectors, I'm going to write it like that. I want to find the velocity, so that's what I want to find, so I'm going to call that just A and B. I've just worked out the acceleration. That was 3, 4. And it's after 7 seconds. So I know that I'm going to use the V equals U plus AT Suvat equation, but I'm going to do it in terms of vectors this time. So I'm going to deal with the horizontal numbers first. So A is equal to 0 plus 3 lots of 7, so that's 21. And B is going to be 0 plus 4 lots of 28. So that's the velocity. If it had asked me for the magnitude, then I would have done my little picture and worked out that length. And if it asked for the angle, I would have done that as well, but it didn't. It asked in this case for the velocity vector after 7 seconds. See if you can work out how far the particle travels in the first 4 seconds, part C. I would work out S as a vector, but how far, they want to know its magnitude. Pause and have a go at that bit. Okay, so here's my SUVAT setup. I'm trying to find the distance. I'm going to work it out as a vector. Initial velocity 0. Acceleration is still the same from part A, work that out. And they want to know this time after 4 seconds. So this was the formula I used. U is 0, so that term disappears. So you get a half a t squared, 4 squared 16. Half of 16 is 8, so it's 8 times that, which gives me that. That's the distance as a vector, so I sketched it and worked out its magnitude. Didn't ask for the angle, so that was my answer, 40 meters per second. Okay, so part D, a third force is applied to the particle, and we've got a new acceleration. So we're back to F equals ma here. So what I'm going to do is I'm going to say, right, well, its mass is still 3. Its acceleration is now. So what must the resultant force of now these 3 forces be? So the resultant force has got to be... So let's remember where this force is coming from. This force is that one, plus this new one. So I know that 12 minus 4 plus minus 3, 16, plus this new mystery force has to equal that. So it's fairly straightforward, isn't it? So 21 take away 3 is 9. So A has to be 12. So this is the force K we're working out. And minus 4 plus 16 is 12. I need it to be minus 6, so that's minus 18. And I note that they ask for it in terms of I and J, so okay. I'll do what I'm told. There we go. Good stuff. Okay, so 2 questions for you to try, both of which you'll find in the mechanics textbook I've given you, but they're on the screen here anyway. Those of you in yesterday's lesson may already have done this one, so a little bit less work for you to do. You are welcome to check the answers yourself, and if you get them right, that's fine. However, I'm going to come back in a minute and go through these 2 questions. Okay. If you are not going to watch those solutions because you feel confident you've got them right, remember that it is important that you watch the momentum video. I'm going to take my time over that one, so it's nice and thorough. So that will probably be coming out later on this afternoon. Okay, wind's starting to howl a bit now, so I'll go through this first one before I go and check my greenhouse. At first reading, you're thinking, why are they telling me about G? And I mean, it's a bit frustrating they're making it equal to 10. Well, that's because they give you the weight of the wheelie bin, and actually we need the mass of the wheelie bin. So that was the thing there. Now, I don't know if you tried to sketch the 2 forces. You don't really need to, do you? You know, I made a fairly poor attempt here at getting the rough directions of those 2 forces, but we don't know where they're being applied. So the key thing is that those 2 forces have this as their resultant. And if the mass is 40, the acceleration must be this, because 40 times 0.3 is 12, and 40 times minus 0.1 is minus 4. So that's the acceleration. And I guess because the question uses I and J notation, I'm in sort of belt and braces territory here, but I'm going to use I and J notation in my final answer. And I sort of put that in brackets like they've done, just following their lead. We're then asked 2 things about how far it travels. We're asked for the displacement as a vector. So here's my SUVAT setup, trying to find the displacement, know the acceleration, know the time, and know the initial velocity was 0. So So I used s equals ut plus half et squared, but u is 0, so that disappears. And so this number is just a half times 0.3 times 25, and this number is a half times minus 0.1 times 25. Bang, bang. That's the answer to that first part. It then says what's the distance, so that's just the magnitude of that displacement. So, and I gave it in surd form and as a rounded decimal. Okay, that's that one. So here is the second of those two questions. Sorry, I've just spent an hour mending the greenhouse, so that's why the video is a little delayed this morning, sorry. Anyway, so we're told the resultant force and two of the other forces, and we have to work out the third one, so it's just a simple subtraction sum. Hopefully you were okay with that. And then we knew the resultant force all along, so we can use that in F equals ma. Mass was 2.5 kilograms, so F equals ma, so the acceleration was 0.4, which I then used in SUVAT. We were asked to find the distance travelled in the first 4 seconds, so I worked out the distance as a vector using s equals ut plus a half at squared. As before, u is 0, so it's nice and easy. And then, having worked out the displacement vector, I used Pythagoras to work out the actual distance travelled. Okay, so that's the end of that video. I will make the moments video later today and make sure that you have a look at that at some point over half term. Take care.